A warm greetings to one and all. In this session, let's learn about HMM backward algorithm with an solved example problem. As a part of introduction, we should know that HMM backward algorithm is similar to forward algorithm, but it goes backward in time as its name suggested. It is essential because it efficiently calculates the probability of future observation in given a sequence of past observation. It also complements the forward algorithm by providing the way to evaluate the likelihood of observing a sequence from any given state, which is crucial for updating the model parameters. It also uses the dynamic programming to enhance the computational efficiency. It helps in managing the uncertainty of hidden states, especially during the EM process for parameter estimation when the full state sequence is not known.
Now let's learn about HMM forward algorithm. The inputs required are observations, that is, a sequence of observed event which is represented as capital O, which is equivalent to O1, O2 up to OT. These represents a sequence of events where O1, O2, OT are individual observed events at time t is equal to 1, 2 up to capital T. The next comes states. A set of hidden states which is represented as capital S is equivalent to S1, S2 up to Sn. So these are the hidden or unobservable states in the system. Next comes the initial probability which is represented as pi which is equivalent to pi of S1, pi of S2, pi of Sn, where pi of S1 is the probability of starting in state S1, similarly S2 and Sn. The sum of all the initial probability must be equivalent to 1. The next comes transition probability, which is represented as small a, which is equivalent to probability of S1 to Sj. That is, this represents the probability of transition from one state to other state, that is from Si state to Sj state. So, these probabilities are often represented in a transition matrix. Next, emission probabilities. It is represented as small b, which is equivalent to probability of OT given Sj. This represents the probability of observing a particular event given a hidden state, where b is the probability of observing the event OT at the time t given the system is in state Sj at that time. So these probabilities are often represented as emission matrix.
The first step in HMM backward algorithm is initialization step. Here, for each state I, we need to initialize the backward probability beta t of I is equivalent to 1. The next step is recursion. Here, we need to calculate the backward probability beta t of I from time t minus 1 to 1 in each state I. And the formula used is summation j is equivalent to 1 to n aij into bj of O t plus 1 into backward probability t plus 1 of j, that is beta of t plus 1 of j. The third step is termination step. Here, the total probability of the observation sequence O is derived from HMM parameter lambda. That is, probability of O given lambda is equivalent to summation of I is equivalent to 1 to n pi of I into bi of O1 into beta 1 of I. This approach captures a recursive nature of backward algorithm using transition probability Aij and emission probability Bi of Ot plus 1 to update the backward probabilities at each time step. Let's solve the problem using HMM backward algorithm. Let's consider Raja. He may be happy or sad, which is the observed sequence. So we need to calculate the backward probability of observing the sequence happy to sad based on the given model. So we need to calculate what is the likelihood of observing this mood sequence under the given weather states.
Now let's check out the properties of hidden Markov model based on our example. Here, the first comes hidden state capital S. It represents the hidden state sunny and rainy as S of sunny and S of rainy. The next comes observable O. So in our example, we have two observables, namely happy and sad, which is represented as O of happy and O of sad. Next, the initial probability pi represents the value of sunny as 0.6 and the value of rainy as 0.4 as per our example is mentioned here. Next, the initial likelihood of the state at time t is equal to 0 is considered in our example. The next property is transition probability. The transition probability is a matrix that represents the probability of transition from one hidden state to another hidden state. So it is represented by small a. Since we have two hidden states in our model, namely sunny and rainy, we have 2 by 2 matrix. So depending upon the number of hidden states, the matrix size may vary. Here, the matrix value A11 represents the transition from sunny to sunny. Its value is mentioned as 0.8 in our model. Next, the matrix value A12 represents the transition from sunny to rainy. Its value is mentioned as 0.2 in our model. Next, the matrix value A21 represents the transition from rainy to sunny. Its value is mentioned as 0.4 in our model. The matrix value A22 represents the transition from rainy to rainy. Its value is mentioned as 0.6 in our model. The next property is emission probability. Emission probability represents the probability of seeing a specific observables given a hidden state. Here we represent both hidden states and observable states. In our model, we have two hidden states and two observable states. Emission probability is represented as small b. Here we have 2 by 2 matrix. Since we have two hidden states and two observable states, the matrix size is 2 by 2. So depending upon the hidden states and observables, the matrix size may vary. Here, the matrix value B11 represents the probability of Raja being happy during sunny. So probability of Raja being happy during sunny, the value is 0.8 in our model. Next, the matrix value B12 represents the probability of Raja being sad during sunny. Raja being sad during sunny, the value is 0.2 in our model. Next, the matrix value B21 represents the probability of Raja being happy during rainy. The value is 0.3 in our model. The matrix value B22 represents the Raja being sad during rainy. The value is 0.7 in our model. So finally, every row of matrix must have some value as 1 since they represents the probability. So the initial probability pi also we can see here the value is 0.6 and 0.4. The sum value is 1. In transition probability the first row is 0.8, 0.2, the sum is 1, and 0.4, 0.6, the sum is 1. In emission probability the first row we can see here 0.2, 0.8. So the sum value is 1. Similarly, the next row 0.3 and 0.7, the sum value is 1. So hope you are clear in the properties of hidden Markov model based on our model given here for this example.
Now let's consider the observed sequence of Raja's mood as happy to sad, which is represented as probability of O given lambda model, which is represented here as observable happy, observable sad. That is O of happy, O of sad. We need to find the likelihood for this observation sequence to be derived from HMM using backward algorithm. In order to solve our problem, the first step is initialization step. Yes, this is a model for our example problem. We have the transition probability matrix A and emission probability matrix B as input. The general formula is beta t of I is equivalent to 1. We need to initialize the backward probability for all the available states as 1 at timestamp t. We have the observation sequence O as happy and sad in our model. Since the second observation is sad, let's consider the timestamp 2 here. So we can assign the initial values for both the states sunny and rainy as beta 2 of sunny is equivalent to 1 and beta 2 of rainy is equivalent to 1. And the same is given in the pictorial representation here. The next step is recursion step. The general formula for calculating the backward variable is beta t of I is equal to summation j is equal to 1 to n aij into bj of ot plus 1 into beta of t plus 1 of j. So by substituting the values of I, j and t, we get the formula as a11 into b1 of O2 into beta 2 of 1 plus a12 into b2 of O2 into beta 2 of 2. Here, beta 1 of 1 represents the first backward variable for the state sunny. A11 represents the transition probability from day being sunny to sunny. B1 of O2 represents the emission probability of Raja being sad and the day is sunny. Beta 2 of 1 represents the second backward variable for the state sunny. A12 represents the transition probability from the day is being sunny to rainy. Next, B2 of O2, that is the emission probability from Raja being sad and the day is also rainy. Next, beta 2 of 2 represents the second backward variable for the state rainy. Now we can substitute the values. The transition probability from sunny to sunny, the value is 0.8. The emission probability B of sad given sunny is 0.2, and beta 2 of 1, that is the second backward variable for the state sunny, is 1. It is added with the transition probability sunny to rainy. Sunny to rainy, the value is 0.2, and the emission probability sad given rainy. The emission probability sad given rainy is 0.7. Similarly, the second backward variable for the state rainy is 1. So now by substituting these values, we get the first backward variable for the state sunny is 0.3. The same is given in the pictorial representation here. Now we can calculate for the first backward variable for rainy. The formula for calculating the first backward variable for the state rainy is A21 into B1 of O2 into beta 2 of 1 plus A22 into B2 of O2 into beta 2 of 2. Now we can substitute the corresponding variables. Beta 1 of 2 represents the first backward variable of the state rainy. A21 represents the transition probability from the state rainy to sunny. B1 of O2 represents the emission probability of sad given sunny. B2 of 1 represents the second backward variable for the state sunny. A22 represents the transition probability from the state rainy to rainy. B2 of O2 represents the emission probability for sad given rainy. B2 of 2 represents the second backward variable for the state rainy. Now let's substitute the values for the same. The transition probability for rainy to sunny. The transition probability from rainy to sunny, the value is 0.4. The emission probability for sad given sunny. The emission probability for sad given sunny, the value is 0.2. Beta 2 of sunny, the value is 1. Then the transition probability from rainy to rainy. The transition probability from rainy to rainy, the value is 0.6. The emission probability sad given rainy, the value is 0.7, and B2 of rainy, the value is 1. So by substituting these values, we get the final value as 0.50. So hope you are clear in recursion step. Step 3 is final calculation of total probability. Yes, the total probability of the observation sequence happy, sad is calculated by the formula P of O given lambda, which is equivalent to summation I is equivalent to 1 to n pi I into bi of O1 into beta 1 of I. The initial probabilities, we know that the pi value for sunny is 0.6 and pi value for rainy is 0.4 as per our model. The emission probability for being happy, that is B of happy given sunny, is 0.8 as per our model. Similarly, B of happy given rainy. B of happy given rainy, the value is 0.3 as per our model. The backward probability at t is equivalent to 1 for the state sunny is 0.3 and for the state rainy is 0.5. We know that, which we have calculated in the previous step. By substituting the I value in this general formula, we get the formula as pi of 1 into B1 of O1 into beta 1 of 1 plus pi of 2 into B2 of O1 plus beta 1 of 2. So by substituting the variables for this, we get pi of sunny into B of happy given sunny into beta 1 of sunny plus pi of rainy into B of happy given rainy into beta 1 of rainy. So now we can substitute the values. We know that pi of sunny, the value is 0.6. Then B of happy given sunny, the value is 0.8. Beta 1 of sunny, the value is 0.3. Pi of rainy, the value is 0.4. B of happy given rainy, the value is 0.3. For beta 1 of rainy, the value is 0.5. So by substituting this value, we get the final value as 0.204. The same is given in this pictorial representation here. The final solution by using the HMM backward algorithm for the probability of mood sequence of Raja from happy to sad is 0.204. So hope you are clear in this HMM backward algorithm using this example problem.
Thank you all.